Last night, I gave a talk on Jugglebot as part of the Reddit Robotics Showcase. In this talk, I covered everything from the very first inception of the design all the way up to where it currently is now. And I figured that sharing this talk on my channel would be a good way to catch up anyone who's relatively new to the project, as well as to show you some things that I haven't included in any videos so far. So, without further ado, sit back, relax, and I hope you enjoy the talk. As always, please feel free to leave any comments or questions down below. Enjoy! So this is my project Deep Blue Juggling. And before we get into what the actual robot itself is, it's probably worth answering the question that I imagine is probably on some people's minds, which is, why am I even doing this? And the long story short is that I've been juggling for a bit over 10 years. I studied mechanical engineering at university. I got about a year and a half into doing a PhD on haptic feedback, and then COVID and a bunch of other things happened. And I decided that it would be more interesting to spend my time building a juggling robot. To understand the robot itself, I think it's useful to break it down into 4 main subsystems that roughly correspond to systems that humans use to juggle. And these are the arm, that is responsible for the large, gross movements, the hand, which is responsible for the actual catching and the throwing of the ball. Once the ball is thrown, you need eyes to see where the ball is. And then to actually get the whole thing moving, you need a brain. So let's have a look at all of these in a little bit more detail now. First up is the arm. And something that was really helpful with figuring out some design requirements for this component is that while I was in uni, I did a course that was based on biomechanics. And I got some motion tracking data of me juggling, which has been very nice because it's let me put together some plots of, for example, how far my wrist moves doing different numbers of balls. But to actually break this down further into what the arm itself needs to do, I'm going to propose that we get rid of the Z component, the vertical up and down. That will make a little bit more sense later once we understand how the hand works. But as far as the arm is concerned, we only really care about left and right and forwards and backward movements. And for a couple of reasons, but they don't really matter too much, I decided that 5 balls was a good sort of goal number to be able to do. And that gave me a limit of 0.3 meters in the X and Y direction that the robot needs to be able to cover so that it can juggle the way that I juggle without the balls colliding with each other in the air. Now, some other data that I got from this experiment, or this tracking data, was the frequency, the rate at which balls were being thrown. And this is really useful because it informs how fast the robot needs to be able to move around to catch and throw the balls fast enough so they don't collide with each other. And again, 5 balls is a good sort of rough baseline, and that gives us a frequency of 2 hertz. So that means that there are 2 throws happening every single second, which means it needs to go from the throwing position to the catching position and back again 2 times every single second, meaning that the robot needs to move at least 1.2 meters per second. Not only that, it has to also be precise and move in at least 3 degrees of freedom to be able to throw the ball properly. After a bit of umming and ahhing, I came up with the design of a 6-degree freedom parallel mechanism, which is often called a Stewart platform. And this image here was from Wikipedia of these Stewart platforms. And I've spent a lot of time looking at that GIF. I quite like it. And this is good, but it raised a couple more questions of what geometry do I actually want to use for this platform, and how do I want to actuate it? For the first of these questions, I made a simulation that essentially plotted a ton of points in a volume and moved the upper part of the platform around. And for every point, it checked if all of the legs of the actuator, if all of the legs of the robot, which are, if this lets me draw, these guys here, it checks to make sure that they are all within their allowable length ranges. And if they are, then it plots the point as being green and it is deemed reachable. If one of the legs is either too long or too short, then it is unreachable and it's one of these red points. Now this is good, but it doesn't really allow me to check different geometries very quickly and easily. Importantly, what I was interested in is what angle should I have between the nodes down here, and what angle should I have between the nodes up the top? And also, how big should the base be compared to how big the top is. I didn't really know what this should be. I could have looked at what this diagram was telling me from Wikipedia, but I didn't because I'm a fool. But I wanted to know for myself what they would actually, like what would be the best. And so I made a simulation that just ran this thousands and thousands of times. I can't remember the exact numbers off the top of my head now, but this took like 2 days to run and it was pretty nuts. And what this told me is that all of the angles should be 60 degrees and that the base and the platform should be the exact same size. And this will give the largest reach rate. I thought, cool, this is great. Let's see what that actually looks like. Straight away, I thought, wow, that's awesome. This has like 4 times as much reach rate as this other one that I had. So this should be great. So then I built it and it was extremely unstable because I did not include stability in my criteria that I was checking against. So what I did is I basically just scrapped all of this and did what Wikipedia was telling me to do and made the nodes as close to each other as possible, and the 2 radii, the base radius and the platform radius, made them the same. So that's the geometry done, but now I needed to know how to actually actuate the robot. And what I did for this is, it's a bit of a long story. My first design involved syringes and was clunky at best. It was, kind of questionable. My second design used some store-bought linear actuators that I got off of AliExpress. And this was cool, but they were really weak and really slow. My next design used some ball screws that I put together, some stepper motors with ball screws. They were also very slow, but they were super, super strong. And that was really satisfying getting that working. I had a bit of a dark period after that. Once I realized that was too slow, I tried a lot of different things, some more questionable than others, before I landed on this design, which used strings to actuate the legs up and down. This, after a little bit more improvement, took me to my current design for the actuators, which involves a 150 kV brushless DC motor that is collinear with the extension axis. The motor is this, you can just see the R of the label there, that's the motor, this black bit down here. There are 2 strings, one acts to extend the actuator and one compresses the actuator, and each string has 3 pulleys to route it around in its correct path. I think this design looks really cool, but of course looks are not everything, so we need to know how well it performs. And my last design, which was very similar to this, it shares a lot of components the same as what this design does, was able to reach 2.6 meters per second. And this shitty prototype that I made for this new design lasted 39,000 cycles before one of the strings broke. Thankfully, it broke in a way that is relatively easy to fix, and for my next prototype, that should be resolved, and I expect it should be able to last a lot longer. I'm just waiting on some carbon fiber tubes to be able to make a proper prototype for this. Once that's made, I plan on testing or measuring the power by fixing a mass to the end of the actuator, and we can calculate power by force times velocity, where force is the mass times the acceleration. So that should let me calculate the maximum power and the average power and all this sort of stuff of the actuator. I also plan on measuring the precision by moving it to a known position, measuring exactly where it is with my calipers, moving it around a bit, returning it back to where it was before, and seeing if it actually is where it was, or where it's supposed to be. I'm very interested in this one because precision is quite important for juggling. So we will see. So 6 of those go together to form the Stewart platform of the arm of Jugglebot. And now let's have a look at the hand. The first thing we need to do is figure out what the design requirements of this component are. And this component needs to have a very solid grasp of the ball during the hold. If it is not grasping the ball really solidly, then it will slip and the whole thing will fall apart. It also, of course, needs to catch and throw the ball. But how high? Well, I turned to this very interesting book called The Mathematics of Juggling. And in this book, there's a table of how high throws need to be made to basically not have collisions, and if the throws are being made at a certain rate. And again, 5 balls, good benchmark. So I just said at least 1 meter high. I think if humans can do it at 1.2 meters, a robot should be fine at 1 meter. And with some very basic math, we can figure out that this means the ball needs to be thrown at 4.4 meters per second. Similar to the arm, there were quite a few iterations on the hand. I actually don't have footage of all of the designs that I made, but the first design that I do have footage of is this one that had this sort of like lobed cams to launch the ball up. Now this obviously doesn't have a very solid grasp of the ball while it's being held. It's just very tenuously held in there, but it did do a decent job of throwing. There are a couple issues with it though, and so I changed the design to this that involved this like cup part in the middle, moving up and down, guided by 3 rails. And this cup part would be pulled up and down by a string that ties on down here and goes up over these pulleys. And that design was good. I'm glad that I did it, but it wasn't the best. I then had a bit of a foray into compliant mechanisms, and that was fun, but not the most relevant for this project, I soon found out. And that finally took me on to the precursor to my current design, which works really, really well. I'm constantly surprised by this. It's really cool. The way that this works is we have strings that are shown here in green that are routed from the base of the robot to the base of the hand. And as the arm moves around, these strings are pulled, raising this central cup part. And then these springs, which are shown here in pink, act to pull the cup part back to the hand, back to like the base of the hand. I think this is probably easiest to just show you in with my current one here, that this actually does work. It's really neat. If I just pull this string here, it pulls that cup part up, launching the ball. Super smooth, super satisfying. I'm a big fan of it. So that's how the hand works. And now let's have a look at the eyes. The design requirements of the eyes. I'm a little less certain of any of these because I don't have any experience doing any computer vision stuff, but I knew that it needed to track the balls as quickly as possible, as precisely as possible. Cheaper is good because I'm not made of money. And I would also like it to be portable because I want to be able to move Jugglebot around into different places and juggle in different environments. I think would be cool. I would also really like if it was compatible with standard juggling balls so that I can just like juggle with it, with like me and it in a performance together. I think would be kind of neat. And these were my main sort of criteria that I was comparing my different eye options. And to have a look at what some of those were, the first one was the OptiTrack system, which for anyone who's unfamiliar with it is basically like the gold standard of motion tracking systems in like entertainment industry and everything. It's nuts. It is obviously extremely fast, extremely precise, and extremely expensive, as well as not really being portable and not really being compatible. I would have to move all of these cameras around to the space that Jugglebot is acting in, and I don't have any experience with any of these systems really, but I would guess that I would have to either use custom balls or like spray paint balls with like retroreflective paint or something. It wouldn't be just a drop in with normal juggling balls. The next one that I considered was using these Tundra trackers with the Steam VR lighthouses. And so these are little trackers that are used for VR. I think people use them for like body tracking in VR. And these systems this is quite fast. I think it can do around 100 hertz. It's fairly precise. It's not as precise as the OptiTrack, but it's pretty good. The cost it's kind of expensive. I think it's a couple $100 for each of the trackers as well as the lighthouse. But I already own them, so that's not too bad. It's somewhat portable because the lighthouses are relatively easy to move around, but again, it's not really compatible because the way that this would work is I would print a sort of Voronoi ball that the tracker would go inside, and that way the camera can still, or the lighthouses can still see it through these holes, and it still retains a ball shape. So that would be extremely custom balls, and I don't know, that would be a bit of work, I think, to get the tracker to be in here without interfering with the tracking itself. So that's a not hugely compatible design. And the final design, well, the final product that I was contemplating is these Oak D light depth cameras. These are sort of fast. They should be able to do 120 hertz if everything's set up properly. I have no idea how precise I should expect them to be. I'm going to guess less precise than the other ones. They are the cheapest, and I already own some. And they are the most portable and the most compatible because it's all just working with computer vision. So it doesn't, like, I can just use normal balls. I can just teach it or calibrate it to use normal juggling balls. And this was my favorite of the three options, and that's what I'm moving forward with. And this is what it looks like right now. So this sort of blue, transparent or translucent volume is the field of view of the camera, which you can see is mounted down here. And this is what it looks like when it is tracking. For some reason, PowerPoint has really kind of throttled all of my GIFs, so you can't really see this very well here. But the way that this is working is it's applying a filter on the HSV stream in this image here, fitting a circle to that mask, and then finding the depth data from that circle, like the average depth of that circle. I do need to do a bit more testing just to see if this is working properly and to try to speed it up a bit, but it looks like it's working relatively well to me so far. So that's how the eyes work. Now let's have a look at the brain. Now, the high-level overview of what the brain needs to do is it needs to take the data from the eyes and tell the arm where to go and when to go there. I see that there's two ways to do this. There's the old school way, involving hard coding everything, which would involve, for my purposes, an occipital cortex, if you'll allow some more biological analogies, whose job it is to get the true position of the ball, because any sensor tracking is not going to be perfectly correct. So this wants to get, well, the job of the occipital cortex is to figure out exactly where the ball actually is. We then have a frontal cortex, whose job it is to create a path for the hand and the arm to follow to make sure that it can be where it needs to be at the right time to then either catch or throw the next ball. And there's a motor cortex that actually commands the robot itself to move around. That's the old school way. I think it's relatively likely that at some point I will try option 2, which is just to get AI to do all of this. And I'll go into that a little bit. I'll go into that in more detail in just a sec. The way that I have the occipital cortex working is that it's taking in the noisy tracking data from the eyes, applying a Kalman filter, which basically combines what should be happening based on the known launch, like the throw position and velocity, combines that with the observed noisy data from the eyes. And it combines those to predict what the landing position should be. And you can see it works pretty well, I think. And as the more data comes in, it's more able to calibrate to a approximately correct landing position. And if you're interested, this simulation was run with up to 10 centimeters of noise for each data point, which is pretty big in my mind. I really hope that the depth cameras can be more precise than 10 centimeters. That's a lot of noise. It's also going at 100 frames per second, and the launch velocity is incorrect by 0.1 meters per second in the X and Y direction. So I think that overall the Kalman filter is doing quite a good job at accommodating for those inaccuracies, and it gets pretty close at the end. The frontal cortex, its job is to take in where the ball should be landing or where it should be thrown from, as well as the velocity of the catch or the throw, and also takes in the status of the hand, whether it is currently holding a ball or currently empty, as well as the hand's position. And then it figures out what the hand needs to do next. And this was actually a lot trickier than I was expecting it to be, because something that's really, really important with juggling is that all of the catches and throws are really smooth. Everything has to be smooth. If there's any jagged, abrupt catch or anything, then it's not going to work. It needs to be very, very smooth. And so the way that I did this is using 4-point Bezier curves. So the hold path and the empty path are made by these 4-point Bezier curves, which ensure tangency with the incoming or outgoing ball. And finally, we have the motor cortex, whose job it is basically just to tell the motors what to do. This is definitely the simplest one. I'm using 3 O-Drive V3.6s, And I hope that they will be able to update the position of the motor at 1 kilohertz. I've never done anything like this before, so I don't know what speed to use. I just heard that Boston Dynamics does 1 kilohertz, so I'm gonna lead from their example and try to do that. Now that's if I was doing everything the traditional way. I think it would be cool to do AI stuff, and what I would probably do with that is using NVIDIA Isaac Gym, just because I've seen the most about that. I know there are other options, and I'd be very interested to learn if there would be anything more appropriate, but this seems like a pretty set up system. And hopefully, if I can get one, I would love to use an NVIDIA Jetson or a Nano, because these things seem absolutely nuts for what they can do. But we'll see. The next few steps for the project are to calibrate my depth cameras, just to make sure that they are actually correct, to build and test the new linear actuators, because I need to make sure that they work, and as soon as I get my carbon fiber tubes, I'll be building them. I need to solve a CAN issue, because my CAN system is not working, and I would love, if anyone is familiar with CAN, hit me up. Yeah, I'm having problems with that, but I think it should be okay. And I don't really know what else. Some other things will probably come after this, but eventually it should be able to juggle, hopefully soon. 2 long-term goals for the project. One is to beat the world record for ball juggling, which is 14 balls and 14 catches, which is absolutely nuts. I have no idea how this guy can do this. It's insane. And the other one is to get a troop of Jugglebots, a whole collection of them, all juggling together with LED or glowing balls, in time to music, with a drone flying through. I think this would be absolutely insane, like the Tesla factory style drone thing flying through, have it all choreographed. I think that would be absolutely nuts. And that's it. So thank you for watching, and I am open to any questions that you've got.
Oh, that was fantastic.
Yeah, that was really great.
Cool. Personally, I always get nervous about these events, and in the run-up to it, thinking, "Oh, is the effort and the time I put into it worth it? Am I going to enjoy it?" And then, as soon as the presentations start, that's a really good one to start on as well. That was really cool. Great presentation. My PhD is related to compliance actuators. There was a lot of stuff I found very interesting there too. You've got compliments for the quality of your Kalman feature as well. And yeah, there's lots of interesting questions about the vision stuff as well. I really, really like the idea, the long-term goals you have. The idea of getting multiple to juggle together. I will let Michael,
it's gonna be awesome.
Ask a couple of questions from the chat, if that's okay.
Yeah, absolutely. You got it. So our first question is about the tension on the actuators, on the strings for the actuators. So how do you keep tension on the strings for the actuators, and specifically for the catch throw actuator, how do you keep tension on that while it's, moving around in 6 degrees of freedom all the time?
That is a good question. So I'll answer. I'll talk about the hand first. So this guy, the hand, I have the string, I will have the string set up so that it is like tight at when the Jugglebot is like at the bottom, and then so it can only ever go up, basically. It will never become more slack on this string. It will mean that will almost certainly limit how far the arm can move around, because this will like hit its length limit before the rest of the robot will. So that will put a bit more of an imposition on the range of motion of the whole robot, but I think it should be okay. And I've got a couple ideas of like gearing this down to accommodate for that. But yeah, it's essentially, it can't become more slack. And just to answer for keeping the strings tight in general, I don't have one tied onto here currently, but the way that I'm like fixing them onto the end is the string goes through a little hole and I wrap it around. It's not focusing. There's a little bolt there. So the string passes through, there's a small hole, if I can get it to show, right next to the bolt. And basically the string comes up, wraps around the bolt, and then I just tie the bolt, or like tighten the bolt in, and it will like clamp it up. So if anything does get loose, it's just loosen the bolt, pull the string, tighten the bolt back up again. And it's really quick.
Okay. Very cool. Someone asked, you base your assumptions on the speeds and heights of the balls on, your motion capture for human juggling. Do you expect that that's going to be the optimal value for a robot juggling, or do you think there's something different about robots juggling that might cause those values to be different?
I think it is a conservative guess. I think that the robot will be better. I think the only reason, it's like when you see someone do something really well, you think, wow, that looks effortless. It looks like they're not doing anything. Like, and when you really get like in the zone and you're juggling, it's really no effort at all. You just keep it going, just keep it smooth. And I think a big part of the reason why humans find such a hard time with juggling is that we just can't do things that consistently, but robots can, in my understanding. So I think that it will be more, it will have a tighter pattern, and I think it will be able to like shrink those limits down a lot. So I think that what I've based all this on, like the 0.3 meters XY, all of this stuff, I think is very conservative. Yeah. I think if it can do those range of motion and that speed and everything, then it should very easily be able to juggle better than I can.
That's very interesting. Um,
Can I ask a question?
Please go ahead.
Yeah.
I really liked, the whole way you've approached the project is really good. Frankly, I like the way you've gone about the not AI route first, because it means that you're going to have lots of really reliable data and solutions that work and how well they work, and rather than asking your AI, it will magically solve everything.
Yeah. The black box.
Target. This is the problem I can't solve, but these are reliable data I can use to develop a solution for. I can very much see some reinforcement learning going a long way there to juggling. And the nice thing, you've got simulations too, so you can do a lot of the work in simulation for very little money before you commit to buying.
Oh, I think we lost you for a second, Ollie.
Yeah. But I do agree. It will be good to be able to test things in sim before buying them. Yeah, my wallet is not loving this project.
Yeah, that is the unfortunate reality of self-funded work, huh?
Yeah.
Yeah. But we have one more question from the YouTube chat, which is, someone said they noticed online that you sometimes refer to the Jugglebot as the, first real or the first proper juggling robot. Now, how do you consider your robot to be different from the other juggling solutions out there?
Yeah, that's a very good question. So there's a really good video by Luke Burrage that I'll post in the comments when I'm done with this, where it's basically like a literature review for this project, and he released it like 6 months before I started on this. It was such good timing. I'm like, wow, like yeah, it was great. But he describes juggling automaton and juggling robots as being separate things, where the automaton are things that are hard coded, and there have been a lot of these that people have made. I think Claude Shannon made the first one, where it's just a mechanism that follows a very predetermined path, and like a person has to load the balls in at the right time, and if it drops, it just keeps on carrying on, happy as Larry. It's got no idea. That's obviously not going to be able to do what I want it to do. So I need it to be a juggling robot where it can actually sense the balls and accommodate for where the balls actually are. And I'm only familiar with one example of a robot that does this, and it's pretty not great. I am fairly confident the people who worked on that are not jugglers themselves, and I think that they just made like arms and a human sort of hand, and they just wanted to like show off what it could do, and so they made it juggle 3 balls, and it's not great. So yeah, I think that this will be the first robot that can actually juggle the way that it can make the balls move the way that humans can make the balls move. Maybe the way that the robot is doing it is quite different to the way the humans do it, but yeah, I think that's where I'm coming at it from.
That's a good definition of that. Yeah.
There's a question from the chat. It's definitely a more long-term goal for you, but when you get it, outdoors, I suppose, do you have any thoughts about how you would account for wind?
Wind is an interesting one.
It's indoor juggling robots.
I don't really think wind is that big of a problem, to be honest. Not with ball juggling. I think this is why I have sort of steered towards ball juggling. Like I used to juggle rings and clubs and stuff as well, but with both of those, if there's a little bit of wind, they just blow away. But the balls are like they're fairly dense and they're fairly small, so they don't really get it, like unless you're in like a hurricane or something, it's pretty fine. And I think with the Kalman filter approach and that sort of thing, I think it should be able to accommodate it pretty well. Or unless it, like if it's throwing like super super high, maybe that guy that got the world record would have a different opinion on wind to me. But
Yeah, breaking the record might require some compensation, but just getting it juggling, yeah, you're right. The density of the ball,
I think it should be fine.
Yeah. There's definitely a range, a working performance range, and then beyond that height, it starts to get more of a factor.
Yeah, and also even with the way that the hands are now, like the space to catch the ball is quite big. Like the ball can very easily fit in there. Like it's got a fair bit of room to mess up. So yeah, I think it'll be okay. I'll have to see.
Yeah. Someone asks, do you have any plans to make it do any other tricks, like, varying the path that it's throwing or changing the number of balls on the fly?
Yeah. Something that I would really like it to be able to do is to juggle. It's a little bit. Just before I answer that, there's a thing that is used to describe juggling patterns. It's called site swap notation, where you can basically encode the pattern with numbers. So, for example, this pattern that I did right at the start with me juggling has a pattern of 6x4, 4, 6x. It's a bit of a weird number, if I can get all the way back there. That one. So that's got a very specific number, and that's the only way that pattern is described is with a number. I don't think it has any actual name other than that. And what I would really like to be able to do is tell Jugglebot to start doing this pattern, and then it can find the path to get to that pattern, and then go into that pattern. There's a lot of stuff involved with that. It's kind of hard to describe, but yes, that is a goal that I would very much like Jugglebot to be able to do, is basically say, do this, and then it will figure out how to get there, and then it will do it. I think that would be very, very cool.
It sounds like a great goal. Yeah.
Yeah, thank you very much, Harrison. Yeah, delightful way to start.
Thank you.